one of the most important parameter measured in the industry or in process. Um, so level measurement uh, determines basically the position of the surface of our material inside a vessel. Uh, so it measure the distance, the surface of the material. Okay, and then if we know the total height of our vessel, we can estimate the actual height of our material inside the vessel or tank. There are many technology can be used and this technology will be based on the characteristic of the material or the fluids inside the vessel. Um, there is no one universal solution for levels transducer because in vessel or in process the material may vary in terms of the properties. It can be like, for example, can be conductive, it can be non-conductive, it can be multi-phase, it can be liquid, and so on. And broadly speaking, there are two main types of level sensors. The first one is the continuous level sensors, and the second one is point level sensor. Uh, for application where continuous level measurement is needed, like our fuel tank and storage container, so the continuous level sensor indicate the fluid level within a range, range of value. But for point measurement or point level sensors, they only indicate low or and high. So mainly today we look into both type of level sensors. So as I said before, there are many type of liquid level measurement methods such as RF, capacitance, okay, conductance, and then also based on pressure difference. So we have based on energy signals, radar, ultrasonic, and some mechanical methods, okay, like float or pedal wheel. Okay, first we look into the concept of RF capacitance. So in this method, basically, RF means the radio frequency capacitance, but the output is basically transmit through a radio frequency. But mainly we will look into the concept of capacitance. In this capacitor method, it will have an electrode sensor. Okay, so electrode sensor, okay, basically a rod. It can be a rod or it can be a concentric rod. Okay, placed inside the center of the tank. Okay, and then the electrode basically placed from the top to the maybe to the lowest point of the inside of the vessel, and then the output of the capacitance is basically transmit to a radio frequency signal. So in this RF capacitor, the electrode, the main sensing electrode, okay, is the in the middle. So that can be the connected to the positive potential, and the vessel itself is made of metal. Okay, metal means like conductive uh, uh, material, and then the vessel body itself is grounded or negatively or, uh, or connected to negative potential. And so in between the electrode and the vessel, so the material will be the insulator. Okay, the uh, material will be the insulator, okay, between the electrode and the main body of the vessel. So it is suitable to detect level of liquids, uh, slurries, or granular, or or anything in interface, especially material with high relative permittivity. It can be for specific point, but usually it is used for continuous level measurement, and the frequency range that is used to submit to transmit the output is in range 30 kilohertz to 1 megahertz. So the concept, okay, the based on the capacitance measured by the electrodes, in between the electrodes, and the vessel body, okay, whereas the capacitance, is proportional to the uh, material or insulating material, okay, or it can be written by uh, epsilon naught epsilon r A over D. Okay, and epsilon r is the relative permittivity, epsilon naught is the constant, A is the surface area of the plates. So let's say in the half full case, so we have two materials, okay, or two capacitance value given by the material, main material, and the air. Okay, so the total capacitance will be determined by the material, okay, in between the electrons, or between the electrons and the body of the vessel. So in a typical application, the tank or the vessel is usually metallic, but in some cases, uh, like we will look into later, so we can make it into a concentric electrode, okay, to measure the capacitance. So if the tank is empty in this case, so the insulating medium in between the electrode and the body or the metallic vessel will be air. But when the tank is full, so means that the insulating medium is the liquid. Okay, so in between So in between means that, let's say half, it means that the capacitance is from the space or the air, and also from the liquid. So the capacitance is measured to provide a direct or linear measurement of the tank. Okay, so the level of the material, okay, can be estimated to to measure the actual height, okay, based on the formula, or based on the capacitance measurement. So in some cases, in some cases, the electrode will when it use the electrode, there will be some build up or deposition of material over the time. Okay. So that deposition of material on around the sensing electrode will cause an error. So the output, okay, will okay, contain or the compounding capacitance of the in the output. So it will have an error, also misreading on to estimate the height. So how to solve the issue here? One of this is by using a regular checkup or regular inspection, okay, or cleaning. So there are other methods like um, reverse electrolysis, okay, that allow to material that deposed to detach from the electrode, but that's require some circuitry or injection of current into the electrode. But one of the typical solution is to perform a regular inspection or cleaning, where we look into the electrode if there are any deposition, so we can remove. Right. So in let's look at this example. In this case, where we don't rely on the vessel body to estimate the height of the material, whereas the okay level of the liquid in the container can be detected by a cylindrical tube capacitor. So it looks like this. The cylindrical tube has a bigger tube with a diameter of D2, and then on the bottom side there's a hole, okay, allowing the material to get inside the tube, the outer tube. So the liquid level, okay, will be the same at the actual level inside the container. And in the middle of the tube, there is another rod, okay, a rod with the diameter D2. So the middle rod is connected to the positive potential, and the cylindrical tube, outside cylindrical tube is connected to negative potential. Okay, of course, the electrode and the tube are made of metal. So the capacitance between the electrode and the cylindrical tube can be measured or estimated, and it is a function of the height, H2, whereas epsilon 2 is the material or the liquid level, and epsilon 1 is the air relative permittivity. Okay, so referring to the figure, we look into how we can derive the equation here. So the final equation is given by this formula. The typical equation or typical formula for the capacitance for the cylindrical capacitor is given by this formula, where L is the total height, L is H1 plus H2 basically. It's a duplicate H1 or H2. And epsilon naught is the permittivity of the free space, which is equal to 8.85 times 10 to the power of negative 12 farad per meter. Epsilon R is the relative permittivity, whether it is liquid or air, and D1 and D2 are the inner and outer concentric cylinder diameter respectively, or D1 and D2. So let's determine the equation. Based on this. So first we need to understand the total capacitance or value is contributed by the capacitance from C1, which is from the air, or epsilon 1, which is the air, and C2 from epsilon 2, or the liquid. Okay, from liquid. Means that the total capacitance C1 plus C2. So the total capacitance is given by C1 plus C2. So we need to figure out the capacitance from C1 and then the capacitance from C2. So capacitance from C1 using this formula, 2 pi epsilon 0 epsilon R multiply with H over long D2 over D1, where epsilon R is equivalent to what? But we can leave it as epsilon R, that's fine. But L is given by H. So L here is H1. For C2, 2 pi, we can write this as epsilon r equivalent to epsilon r1. Okay. So here we get 2 pi epsilon 0 epsilon r1 h1 over ln d2 over d1. For C2 is 2 pi epsilon 0 epsilon r L over ln d2 over d1, where epsilon r is equivalent to epsilon r2 and L is equivalent to h2. So we get 2 pi epsilon 0 epsilon r2 h2 over ln d2 over d1. So finally, C total, okay, from here is equivalent to 2 pi epsilon 0 epsilon r h1 plus ln d2 over d1 plus 2 pi epsilon 0 epsilon 1 2 h2 over ln d2 over d1 equals to 2 pi epsilon 0 epsilon r1 h1 plus epsilon r2 h2 over ln d2 d1. So that's the equation. Okay, so next, calculate the Cx or the C total. So what is the C total value or the Cx? If all the value is given here, so the in two cases, the minimum and half of the water level. Okay, what is the minimum and what's the half? Oh, so T minimum, which means that H1 is equivalent to the total length, or H1 is equal to L, whereas the total of tank height. So minimum means that only air. There's no liquid, minimum, only air. So C total minimum from the equation, 2 pi multiplied with 8.85 times 10 to the power of negative 12 multiply with epsilon 1 1 multiply with 1. So remember that we are measuring in meter. Okay, so this is epsilon r1. So this is L, okay, or h1 plus So I think we need to CT minimum epsilon 0 epsilon 2 pi epsilon 0 epsilon 1 actually h1 plus epsilon 2 h2 over ln d2 over d1. So CT means h1 equals to L, the total height, and h2 is equivalent to 0. Okay, no liquid. So 2 pi times 10 to the power of 12 multiply with 1 plus 1 A, H is 1, 1000 times 10 to the power of 3 meter, because we in meter, epsilon 2 is supposed to be 88, but H2 is 0 meter. Divide by ln 0.02 over 0.01. So that we get 80.22 picofarad. So that's CT min. (80.22 picofarad). CT min. And CT half. So CT half means that for epsilon r 1, H1 is equivalent to L over 2 in meter, and for epsilon R2, H2 is equivalent also L over 2, okay, in meter. So we calculate 1 multiply with 0.5 plus 85 0.5 divide long 0.02 over 0.01. So we get 3.57 nanofarad. Okay, so we have seen that half in half condition, so capacitance have increased, okay, from where city minimum when there is no liquid is 80.22 picofarad. Right. So that's for capacitance. And we look into conductance or conductivity. So this is basically a point measurement application, whereas it only give the outcome of low and maximum, or minimum or maximum. So this is not measuring the continuous level. So this is conductive based on the two conductive electrode. One is longer than the other one. The one set is electrode is placed from the top to the bottom part of the vessel, and then the second one, the length is until the minimum level from the top. This is relatively low cost and simple method. So it's based on the electric conductance. So basically, liquid can conduct current with a low voltage source. Okay, this for point detection. Okay, so when the level reach the upper probe, so switch close to start the discharge, means the water go out. When the level reach the lower, the switch open to stop the pump and then let the liquid to enter the tank. So this is conductive based on the material for point level detection. And then hydrostatic heat. Okay, this application shows a system, a simplified system that use a pressure transmitter to estimate the height level of material inside a vessel. Okay, so there's a pressure transmitter at the bottom part of the tank here. Okay, so it will basically compare the pressure on the bottom on the lowest part of the tank. Okay, measure the lowest part and compare with the pressure at the top or the open area or open point of the tank. So if we mark at the bottom as the pressure as P2 and the pressure at the top as P1, so the pressure difference P2 minus P1 will be proportional, in this approach will be proportional to the height, okay, of the material or the liquid level, where we can complete the equation P2 minus P1 equals to rho G H. Rho is the density of the liquid, G is the gravity, gravity acceleration, and H is the level or height. So this transmitter level pressure transmitter basically measure the pressure difference at the bottom part of the tank and compare with the pressure at the top or the open part of the tank. Okay. So the density and the height, okay, will determine the pressure, or will determine the pressure difference, or determine the P2 minus P1 value. So that is measured by the pressure transmitter. So, okay. So the pressure transmitter, okay, has always is placed at the bottom level. So this is the comparison, the representation, okay, and it will, the liquid or the material, okay, pressure, okay, at the bottom will be measured as the one of the part of the diffusion pressure transmitter, and then the other part of the pressure transmitter will measure the on the top. Okay, so there are two conditions. It can be closed tank or open tank. Okay. So basically, when the tank is open, so means that the HP is measuring the P2, and LP will measure the P1, the pressure. So if the tank is empty, means that P2 minus P1 will be equivalent to 0 Pascal, or 0 pressure. And this is what inside the differential pressure transmitter. So they have a diaphragm capacitive sensor basically, and there are two part of the chamber. On the left chamber will, okay, exposed to the pressure from the liquid, or from the material, or in the vessel, and the second chamber will be exposed to the uh, open air, or the open space, okay, or the low pressure. Okay, basically when the pressure at P2 increase, okay, the capacitive sensor here is flexible. Okay, so it will in the middle, okay, will flex. Okay, what happened? Okay, it will flex, okay, to the right. Okay, and then the capacitance on the left chamber, okay, will change, and also on the right chamber, and in proportional with the right chamber. Okay, so let's say C2 and C1. Okay, so we know that C, the capacitance, is equal to or proportional to the basically the surface area and the distance. Okay, so the what happened, surface area will be fixed, but the distance due to the pressure, okay, will vary. So due to the pressure of P2, capacitance C2 will decrease, and C1 will increase. So those capacitance change, okay, will be calibrated to measure the pressure difference between P2 and P1. Okay, that's how it used to measure the pressure difference using the diaphragm capacitive sensor. Okay, so this, okay, in this figure shows the complete set of the differential capacitance pressure sensor to measure the height, whereas it include temperature transmitter, okay, where in the liquid density, uh, density is the rho, okay, it's basically sensitive to the temperature. So to make sure that the measurement of P2 minus P1 equal to rho GH, where you want to estimate what is the H here, height. So the rho here is in the function of basically the function of the temperature. So need to measure the temperature and estimate the actual density in the function of the temperature lah, so that we can measure the height in much. So the height we measure P2 minus P1 rho G. G is the gravity, and rho here is the density of the material lah. P2 minus 1, the pressure difference is measured by the pressure transmitter. So with this arrangement or the placement of the temperature transmitter will make sure that the estimation of the level height is much accurate. Okay. Okay. Next we discuss about the microwave level transducer. Microwave level transducer, this is a non-intrusive method. Okay, based on microwave signal transmission. So it is designed for continuous level measurement. Basically, for invasive or non-invasive, means that it can be inside the transmitter, or the microwave source can be inside the vessel or can be outside, whereas it can penetrate the tank. But usually it is invasive, invasive, where we have to put inside the tank. So it operates on the principle of beaming microwave downward to us downward from a sensor located on top of the vessel. Okay, so the source, okay, is basically in line with the sensor, and when the microwave is signal or energy is transmitted downward, it will reach the surface of the liquid, and then the echo, okay, will bounce. Okay, will go the signal. Some of the signal will bounce back, and then measured by the sensor or detector. It's and so basically measuring the echo. So the time of the signal travels, okay, from the transmitter to the receiver is called as the time of flight. Okay, or the total time it's travel from the sensor to the surface and back to the receiver. So that is time of flight. So if we know the velocity of the signal or the microwave signal, so we can estimate the total travel. Okay, L. We know that the velocity is equivalent to the total distance divided by the time of flight. So we can estimate the total distance L. But the surface or the distance from the sensor to the surface is half of the total length of the distance traveled by the signal. So L1, which is the top one, is L over 2. Okay, so that we know is what is the distance between the sensor and the surface. Then next we can actually estimate the total height, okay, of the material. Okay, so H will be equivalent to L1, uh, H, capital H, which is the total length of the vessel, minus L1, so that we know the uh, actual height of the material. So this figure show two different type of uh, s- uh, uh, source for the microwave signal. One is parabolic and second one is the cone. So basically parabolic dish direct the signal to wider area, while the cone confine the signal in the much narrow path. Okay, so the choice is to depend on few factor. For example, uh, tank obstruction that may serve the reflector depends on the if they are separator like mixer, okay, like mixer. So that will determine which one we going to use. And also presence of foam. So in some process, so there will be like for example mixing of material or mix. So they usually will create a foam. Okay? So foam also will determine which type of antenna that is much suitable, and also turbulence of the fluid. Okay, and this is one of method how to determine the distance uh, uh, without having to measure the time of flight. Means that it is based on the linear frequency sweep. So this method is called as frequency modulated continuous wave, or FMCW. So it will instead of a fixed frequency of the microwave signal, so it sends a linear frequency sweep. Means that the microwave signal is very or contain many range of frequency in one sweep. So meaning that when the reflector radar is delayed in proportional to the distance of the level, and its frequency is different from that of the transmitted signal, and the two signal blend into a new frequency. Then the new frequency can be converted into a very accurate measure of time. So the transmitted frequency, let's say F1, uh, and then the received signal F0. So uh, the difference between the received signal and the transmit signal will be proportional to the distance. So instead of measuring, knowing the velocity of the microwave signal, so we in this application we vary the frequency of the signals and then measure the trans the reflected frequency, then compare with the frequency that it sends. So that difference can be used to measure the distance or estimate the distance. The advantage of this system is that it is more immune to noise. And then there is another construction of microwave radar signal. In this application, we use the same kind of energy, which is the microwave signal, but the signal is wave guided, means that the signal is transmitted through guiding rods. So in this case, we use a rod to or cable to guide the microwave signal into the material in the tank. Okay, and the height of the material or the height of the material inside the tank, okay, is determined based on the time domain refractory method. So what it do is develop 2,000 pulses of signal, microwave signal, electromagnetic signals through the waveguide, and then measure the reflection. So basically, the dialectic of the fluid will determine the reflection. So in this case, okay, first it will transmit a radar pulse, very high frequency, into the rod. So you see the rod have one set that transmit the signals or the radar pulse, and once the radar pulse reach to the surface, some of the signal will be scattered and reflect, and that reflection will be measured by another set. The set, and then the set will measure how much the pulse is reflected, and then this pulse will travel back to the receiver, and then will be time or estimate the time delay. So they will have a source, okay, like in this figure where source, okay, source signal, and then there will be a reflection. So the distance between the source signal to the reflection, okay, we can measure the distance, okay, d. Okay, so if we know the velocity, okay, and then the d tau, so we can estimate the distance or the distance of travel. This is basically d over 2. Okay, so we can estimate the h is basically the total height minus d over 2. So the advantage of this method, this is wave guided, means that in the presence of foam, okay, or turbulence, we will not affect the measurement. And then it can handle varying specific, means that the rho density material with changing density, also is immune to coating problem. And then the problem is that it is invasive and and intrusive. Means that if the system have a mixer, it's not be suitable lah to place inside. Okay, and also is not suitable for material that is corrosive. So this is the comparison between the FMCR radar and MIR. So the MIR impulse micropower impulse radar basically utilize wave guided signals. Okay, and then it is low power, but FMCR, okay, high energy. Okay, it require high input energy. MIR is much less complexity and lower cost, but FMCW or the radar sensor that based on the transmitted microwave signal will be much more expensive, and the installation may take more time. Okay. Next, we have our ultrasonic sensor. So it is used for continuous level measurement. So basically, this system require installation of ultrasonic sensor on the top of the tank, where the ultrasonic signals in the frequency range between 20 to 200 kilohertz. Okay, basically acoustic signal is transmit on the top. Okay, and then when the signals reach the surface, the echo or some of the wave will be reflected back to the receiver, and the distance or the time of flight of the signal can be used to estimate the actual height of the material if we know the actual height of the tank. Okay, so similar concept by the radar, okay, or time flight, which I have explained. So these are some of the ultrasonic sensors construction. Okay, so need to consider some of the factors when using acoustic signals. Basically, the medium where the signal travel, which is usually air for the ultrasonic, the density may vary with the temperature. So we need to be careful. The temperature must be carefully maintained, and also some cases where in a vessel, okay, where our ultrasonic transmitter and receiver, okay, they will transmit and then receive. So if the material, okay, contain suspended dust, for example, suspended dust, so that actually will cause the acoustic signal to be scattered, okay, in the space or the open space. So we need to remove or reduce the dust. Okay, need to remove or to reduce. Also, in the case of if there are any foam formation, also will affect the measurement, and also in some cases turbulence, whereas the liquid is mixed very in fast, so it will cause us fluctuating readings. Okay, so in to select the best method, so you have to look into the material. If the material is corrosive, for example, is cannot go for, you cannot use a method that use uh, intrusive and invasive like the GWR, uh, guided wave radar, and also you need to know the information, the temperature, the pressure, and then the material. You need to know whether the material, if it is conductive or insulative, highly insulate. So if highly insulate, better use for capacitance method. Okay, and there are the methods, mechanical method. Okay, like this float, what we have in our tank, in our toilet tank. Okay, so I will skip this one, and also the not go right. Okay, so case study, we look into this method, make, okay, in this case, where make powder. Okay, so in this application, you want to measure the height. You need to use something that is non-invasive, means that is sterile. But I show you another example of make processing. Okay, let's look into this example. Okay, uh, in this example is to use or to find a system that can measure the milk uh, level in a vessel. Okay, but in this example, it has predetermined the ultrasonic level transmitter, where we use the acoustic signal to measure the, or to estimate the height. Okay, so the reason why this method is used, because this is milk processing or storage, so it require very hygiene process. So ultrasonic sensor or transmitter basically is non-invasive, And non-intrusive means that the signal has no direct contact on the liquid. Okay, so that determines the hygiene, okay, process. Okay, whereas the sensor is basically placed on top of the vessel, and then measure the estimate the height based on the reflection of this acoustic signal, okay, from the transmitter, okay, to the surface of the milk back to the receiver. Okay, uh, so cannot in this case cannot use a float or something that is directly connect or contact, okay, because it will create a means that there will be bacteria on the contact. Okay, okay, and in this example, so it is the solution or the suggestion is to use ultrasonic transmitter. Okay, uh, and okay, so how in this application, so this has a statement here, forming. So basically, if okay, so if the okay the milk is coming or insert from the top, okay, so the as we know, milk will okay promote formation of foam. Okay, there will be foam or okay on top. So what they do, uh, so what we do, they filling the milk from the bottom. I mean, instead of filling the milk from the top, so there is a pipeline, okay, from the bottom. So the milk coming from the bottom, and then the level rise slowly. So that will be avoiding the formation of foam. Okay, foam. So if there is foam, as we this show before, the foam will cause the acoustic signal to scatter, and then the output, okay, will contain error, okay, because acoustic signal is not a high energy signal, it cannot penetrate foam. Okay, so this solution, the water or the milk is transferred into the tank, okay, from the bottom. But this method require a high pressurized pump. Otherwise, because as the uh, liquid or the material is increasing, so needs more pressure to transfer the liquid. Uh, so to reduce the temperature at flange or transducer of perforated nozzle, I not sure, maybe there's a solution to that perforated nozzle. So some kind of uh, method construction so to avoid and temperature change on the empty space, so that the output or the signal is not affected by the temperature change. Okay, so that is one case, okay, where the uh, ultrasonic ultrasonic transducer can be used to how it can be used to measure the milk level inside a vessel tank. So we have finished our lesson for this week. So next week we will continue on linear displacement and until the next lesson. Okay. So with that, I conclude my lesson or lecture for today. Okay, thank you.
Thank you, Doctor.